We are Purdue Lunabotics, and our faculty advisor is Dr. Nichole Ramirez, and this is our proof of life video for the 2023 NASA Lunabotics competition. The top left screen shows the width of the robot, the bottom left screen shows the length of the robot, and the bottom right shows the height of the robot. In the top right, the robot is being weighed using a standard bathroom scale and some wood supports. 2 pieces of wood as well as a level was used to take each measurement to ensure the farthest points of the robot were chosen and the measurements were accurate. In this video, you can also see our faculty advisor, Dr. Ramirez, verifying these measurements are accurate. The overall dimensions of the robot are as shown. The width was 0.573 meters, the height was 0.590 meters, and the length was 1.09 meters. The weight of the robot, minus the wood supports, was 48.6 kilograms, all within the NASA requirements. This section of the video will highlight the driving capabilities of the robot. On the sand volleyball pit, a 6.9 meter by 2.5 meter mining arena was mapped out, and a collection sieve was placed at the start of the arena. There are 2 craters dug and 3 boulders, represented by buckets placed in the arena. Once the robot reaches the excavation zone and has chosen a mining location, it deploys the excavation system using 2 linear actuators. The robot will spin the mining tool only to show functionality, as we are unable to create the appropriate levels of regolith and gravel in this arena, and therefore the mining operation will be shown using a separate, smaller arena. After mining is completed, the excavation tool is retracted, and the robot returns to storage configuration. Then it will traverse back to the collection sieve to begin the deposition sequence, which will again be shown using the second testing arena. The wheels of the robot are powered by 2 DC motors mounted to the back wheels using a custom-made 90-degree gearbox. The back and front wheels of each side are then mechanically connected via chain. Differential steering between the 2 sides is utilized to navigate the robot around the craters and boulders, as well as align with the collection sieve. This secondary arena features 30 centimeters of a basalt-based granular material developed to mimic the properties of JSCO1 over 15 centimeters of gravel, as well as a collection sieve located in the top right corner. The robot deploys the excavation tool using 2 linear actuators. During deployment, the bucket elevator is also spun to allow for additional clearance with the ground to fully deploy the mining tool. Once the tool is fully deployed, the entire system moves further into the ground using an internal DC motor and lead screw. All these components are protected with plastic and fabric dust covers to ensure no regolith enters the gearboxes. Now that a significant amount of surface-level regolith has been collected, the deposition bin will dump the regolith behind it to make space for gravel. The deposition bin is powered by a rotating arm with a secondary pivot point that is triggered when it hits a hard stop, pulling the connecting cables to therefore rotate the bin. This allows for the contents of the bin to be fully dumped out, making as much room for gravel as possible. The deposition bin will now retract to its original position, so it may continue to collect regolith and gravel. Now the robot resumes mining and lowers itself further into the ground, using the internal lead screw. The rate of descent is adjusted when the gravel layer is reached, which is detected when an increase of the average current of the actuation motor powering the lead screw is seen. The mining tool is a bucket elevator system. It features 13 aluminum buckets bolted to a wide timing belt. The belt is powered by a custom metal 3D printed pulley that, when tensioned, provides a rigid link between the motor and the belt to allow the mining tool to exert sufficient torque to effectively mine the gravel. Now that mining is completed, the excavation system retracts using the internal lead screw. and then using these side-mounted linear actuators, the system is moved back to storage configuration. It is now prepared to drive to the collection sieve. The robot now aligns itself to the collection sieve, ensuring it is as far back as possible and perpendicular with the sieve. The mining tool is once again deployed to allow clearance for the deposition bin to deposit. The bucket elevator is also spun to create additional clearance on the ground to allow for the full deployment of the tool. The deposition bin is now rotated upward to deposit the gravel into the sieve. The bin remains roughly horizontal until the appropriate depositing height is reached. At this point, the secondary arm hits a hard stop, pulling on the connecting cable, which rotates the bin to fully dump its contents into the collection sieve. The mining cycle is now complete. During the mining cycle just shown, 211 grams, or 0.211 kilograms of gravel was collected. In the future testing, more gravel is expected to be collected, as not all the gravel ended up in the sieve. This was due to poor robot positioning and timing of the rotation of the bin. Also, the mining operation was cut short due to a chain becoming in tension. These problems are actively being worked on and are expected to be resolved. Additionally, all operations shown in this video were conducted using manual control. For future demonstrations, we are hoping to have some, if not all, operations conducted autonomously. Dr. Ramirez, our faculty advisor, was unable to verify this collection on video due to an unforeseen family emergency, and will be sending a formal written verification of this collection. Thank you for watching Purdue Lunabotics' official Proof of Life video. We look forward to our live demonstration, as well as seeing all the other teams competing in Tuscaloosa.